Gordon Hamilton, and this is lecture number 2 from Masters Academy and College, Calgary, Alberta, Canada. We started motivating why we're doing this talk by looking at trying to avoid the fate of those which didn't work out well with climate change. So what we want to do is we want to learn more, and that's going to help improve our computer models, and that's going to help predict future climate change, and that's going to help us make, for instance, we might need to move to Antarctic. So if we need to make these big decisions, we want to know about it. Last day I left you with homework, and that was to try to figure out how on earth I could get this kind of temperature data well before thermometers were used in any kind of systematic way. How do I get this kind of temperature information? And I got 4 answers, and I'm going to share 3 of them now and then 1 of them later. The first one was to look at the price of grain or rice in the world. And you would expect that if grain prices are high, that means that the harvest was bad, and that would mean that the climate conditions weren't conducive for growing wheat or barley or rice. So that would be one way to check out on the climate. Another way would be to look at the grape harvests. Harvesting grapes for making wine has gone back thousands of years. Into the Roman Empire, we can check the dates that grape harvests were made. There's a problem with both of those techniques, and that is that it's a complicated matter whenever if the grain harvests aren't sufficient. Is that due to wrong temperature, or is that due to a wrong humidity, not enough rain, for example? So it's a little bit complicated that way. The same is true for dendrochronology. This is a study of tree rings, and the person who got this going is Ellicott Douglas. And so we can find a really old tree, and we can look at the tree rings, and we can imagine that we can count back. So this tree died in 1991, and we can count back through the years, looking at years that there was a lot of tree growth. Those would be years that the temperature and the precipitation were good for growth. And we can look back. So here we see, going back in time, we've already got to 1793. The arrows are pointing out fires. And fire scars can also be used to identify years. So this goes all the way back to 1597. The oldest single tree that we have is the bristlecone pine. And this tree is nearly 5,000 years old. So you can imagine this wood is very, very dense. And you can go back and you can look through the tree rings to assess the climate through those 5,000 years. So there are the 3 measurements of temperature that actually don't use temperature. These are called proxy measurements. So I'm not going to introduce very much new vocabulary, but proxy measurements is a term that I want you to learn. And the idea here is that you're not measuring temperature directly, instead you're relying on a proxy. Okay, let's take another step back. So now I'm going to ask you to go back 11,000 years. How on earth am I going to go back 11,000 years? There's no wine going back 11,000 years. I think the oldest wine might be 8,000 years old. So we're not going to be able to rely on grape harvests. We're not going to be able to rely on written documents. We're not going to be able to rely on a tree, because the oldest tree is less than 5,000 years old. So how on earth are we going to get back that far with an approximation of the temperature? Well, the first idea is to look at dead trees as well as living ones. So what we can do is we can take our live tree, so this tree might be, for example, the one that's 5,000 years old, and we can find a dead tree, and we can match up the rings on those two trees. And that allows us to go back further. We could also find trees that have been cut down and used in furniture or to build houses, and we can also use those pieces of wood to go back even farther. So with this technique, we can actually go back not just 160 years, we can go back to about 10,000 years. So I'm going to squish, I've squished down all of the results that we've had so far, because now we're going to be getting into big climate changes. So now you notice instead of 15 degrees Celsius at the top, I now have 24 degrees Celsius. So you can see all of the variation that we've dealt with so far, that's been squished down to be between 4 and 24. Notice how much of human history is within this time space. All of it. Here, the Vikings landed on Greenland, populated Greenland. Here, this is the first story that was written, the Epic of Gilgamesh, about the same time as that tree. So, now I'm going to go back 400,000 years. You notice I'm using kilo years down below. Kilo is just the abbreviated form for 1,000, so I'm going to go back 400,000 years. How on earth do I do that? First of all, there's no tree samples that I can stitch together to go back anywhere close to that amount of time. I can go back 10,000 years, not 400,000 years. So how on earth do I get temperature data to go back 400,000 years? Well, let's look at water. If you go really up close, you'll find that water is composed of molecules. And let's just look at one of those molecules. That's a molecule of water. It has an oxygen and 2 hydrogens. But the secret is that not all water molecules are the same. The one on the left has got more things in the middle of the oxygen. The oxygen's the red part. So we're going to call that, it's actually got 16 things in the middle. So we'll call that oxygen 16 on the left. And the one on the right has got a little bit more things in the middle. We're going to call that oxygen 18. It's got 18 things in the middle. So those two waters actually behave a little bit differently. You could drink these two and you wouldn't know the difference. I've seen both of those every day. But there is a difference, and the difference comes whenever you're dealing with evaporation. So let's add a little bit of wind here. So this is a warm wind. It's going to create a warm cloud. I know clouds aren't pink, but I've color-coded them for your benefit so that you understand that this is a warm cloud created by warm winds. And what happens with those warm winds? Well, those warm winds pick up both the heavy water, that is with oxygen 18, and the lighter water with oxygen 16. So that cloud will contain both. Whenever that cloud reaches, for example, the Antarctic or the Greenland ice sheets, it comes over, and it drops some, that's snow. So it doesn't look like snow, but it's snow now. And so that cloud has deposited oxygen 18 water and oxygen 16 water.